Good morning, year 13s. How's it going, everybody? Right, so a couple of days more of online teaching and then back to school. I'm going to do my best to try and figure out some kind of recording method to be able to do the rest of each of these series online, because having a complete set is always super useful. So today, guys, we're starting aromatic chemistry, starting with benzene today. I've got a new webcam. There we go. Having a complete set is always super useful. So today, see if I can got cool. So that now seems to be running okay. I've popped out the chat. I can close that. I'm trying some new bits and pieces today. So let's crack on. I'm going to first of all switch my camera to being my overhead one. That should, now you should be able to say, whee, there we go. And then what I'm going to do is I'm going to share my screen and then switch to this one. I think I'm going to give that a try today and see whether or not, because then I can do a bit of dancing around and you guys can still see what I'm doing at this stage. I might just give this a try today, see what it's like. Okay, so what I'm going to do is I'm going to get rid of that YouTube video over there. I've popped out the chat window. Can you guys still hear me okay? I am very aware that my laptop is going to be really kind of, I'm just now swinging all kinds of stuff all over the place. I'm trying to do some weird things here. That's really not helpful. I don't want that. And then, hey, yeah, that kind of works. Right, okay, year 13, you guys are 13D. So we've been working on organics. We were doing some organic naming. Hey, look at that, I can see myself, that's kind of cool. And I can see my own screen, although we'll see how this gets on, no problem. Cool. I'll try my best to be able to then make adjustments to bits and pieces, because it should give me a little bit of a better view now of what's going on. I'm going to switch my computer into tablet mode, down to there. There we go. Right, so I introduced you guys to all the new organic families, and we were just doing some naming at the end of last term. And today we're starting aromatics. So let's go draw. Let's see if we can get back into this. Haven't done this in a while. So this is aromatic A2, aromatic chemistry. I've got to make sure my laptop is cooled. Aromatic. This is where it'd be useful if I can try and adjust the little camera a bit. I don't know what's going on really, to be fair. Is that better? Yeah, a little bit. Okay, aromatic chemistry. Don't know if I actually like the camera being on me or not. Okay, so aromatic chem. So first thing, learning objectives. Number one, now I put these on the YouTube channel itself. So it was number one, no benzene names. Yeah, naming of benzene. Oh no, it's understand, isn't it? It was an understand naming of benzene. Naming of benzene compounds. Benzene compounds. I was focusing primarily on it. And the next one is know your oddities. Know oddities. Because, do you know what, the first learning objective is actually a bit of a stupid learning objective, because benzene just has its own set of rules. And the rules are just a little bit messy. And you pick up these rules and then you add the oddities onto it. And the last one is be able to draw aromatic. Aromatic. I'm going to explain the aromatic thing now, draw aromatic compounds. So, okay. So the first thing we need to do is I need to introduce you guys to benzene. So, subtitle, benzene. Okay, so benzene is a very, very, very important compound when it comes to organic chemistry, because I'm actually a biochemist by trade. My degree was in biochemistry, and one of the things that you learn in biochemistry in a degree is just how important benzene is as a structure. The reason being is that your cells have got the cell membranes and then your nuclear envelope, and if you're building a drug that's going to be having a function in the body or function at a cellular level, which most are, then you have to be able to permeate those membranes. Now, benzene acts a bit like a Swiss Army knife in this regard. The benzene ring is actually locked onto by various transport proteins in cell membranes, which will drag molecules through that membrane. So benzene is like super important when it comes to drugs, because otherwise it'll just float around in your blood, and even being absorbed through the stomach is relatively difficult. But it'll float around, it'll either go pass straight through you, or it'll just remain in your blood system and won't actually do any of its major function. So benzene is super handy for that. So first thing I need to do is need to introduce you to a couple of pictures, because the true picture of benzene is this one. This is benzene, and I cannot stress that enough. I apologize for the crudity of the crudity of the diagram. You can actually, when you take organic chem at university, you actually get pieces of paper with, instead of squared paper, you get hexagonal paper to be able to draw benzene rings. I kid you not. It's kind of cool, actually. I quite like it. But that there is benzene, yeah? And can I just point out that there's no exception to this rule, yeah? Some people often see this picture, often see this one, and think that this is the same thing. And it really isn't. This here is not benzene. Yeah, which is a bit frustrating, really. The top one is benzene. This one here, full name, and you guys can have a go at naming this. So you can pause this now, guys, and you're going to name this with respect to IUPAC. So number one, so you can pause the video now, have a go at naming it. So number one, this is a 6-membered ring. So I can also translate that if you prefer. So this is skeletal, by the way. This is the skeletal diagram. And what we'll now do is we'll now do the displayed one before we really get into the crux of naming this compound. So here's the displayed. And actually, can I just point out the importance of this displayed is really important, because those hydrogens cause so much trouble when it comes to doing MRs of molecules. Students forget this. Can I actually ask you to put in red? This is a super nice nota bene. Yeah, so the nota bene here is that benzene has an MR of 78. MR of 78, and that is super handy. Just to tell you where it comes from, carbon is 12.6, by the way, 78.0, sorry, A level, times by 6, and then 1.0 times by 6. Run that through my calculator. I'd never do anything without a calculator. So the 72 from the carbons plus 6 from those. So the total, of course, being 78.0. Now that's super handy. I'll come back to that as well. Put that in a little bubble. That is super, super useful. I shouldn't really end that nota bene there. Just to now also show you another thing that's super important is benzene as an attachment. This is a phenyl group. So benzene as an attachment. So if I do this, yeah, and I go R, what you now realize is that this structure here has an MR of 77. Yeah, every time you add an R group, you lose a hydrogen in a substitution reaction. Benzene reactions tend to be substitutions rather than additions. And we'll come to that later on in the mechanisms and reactions of benzene. But this one is 77. If I then do another one, which is this one, I'm getting slightly better in my benzenes because I'm doing them slightly smaller. So if I now go R and then R, yeah, we now realize that this one, we can now predict it. This one's going to be an MR of 76. Yeah. Every time we attach, by the way, that's not including the R group. I apologize. This little section here is 76. And then this is super handy because people they try to build MRs in molecules from base up, doing it this method here. But then you realize that this is a really bad shout. Yeah, because you're just going to make a mistake. You're going to add a hydrogen where it shouldn't be. What you do is you learn sections and just be able to tack them together. This is way more useful. And I mean, like, seriously, way more useful. Now, that is one of the best things. Now, I've been teaching A-level chemistry for 15 years. And this little bit here, this little adaptation I made in my teaching came in at about year 8. Because I suddenly realized when I was going through exam reviews with my students, I realized that the students were making super common errors. I was getting only 60% of students giving a correct MR of a compound, and MRs are done in year 9 now at GCSE. For students to be getting this wrong at A2 was just a nightmare. And when I dismantled the whole problem, I realized that this was it. Every time that benzene made an appearance, what happened was that students were simply counting it wrong, adding a H here or taking a H off there. And I realized that teaching 78 is super handy, and then 77, 76, etc. So every time you add an R group, you lose a H, and the benzene section just goes down by 1. Okay, so now we've gone from a skeletal diagram up here. So this one here is your skeletal, and then this one down here is your displayed. Yeah, so this is our displayed formula here. Right, so now everybody's hopefully having a go at naming this. So this now becomes, number 1, it is a cyclo. We know that this is in a ring. Yeah. The next thing is it's a hex. Yeah. Now, this is where things become a little bit tricky, because you pick up at, you don't get this at AS. You do actually. The annoying thing is you kind of do. You get this in nitriles. I should put the name where I pointed the arrow to. So this is cyclohex. Now you want to say at this point, if you had something like, I'm trying to think of something else. If you had something like this, yeah, and you did that, you realize that it's a trichloro. So this is a triene. Now the problem is this is a suffix. Now, when it becomes a suffix, something odd happens. Lots of students will make this mistake. They'll do the dash there, and I do understand why. The problem is it's not, because the ending is a tri suffix. This is a triene. The E has to go back in. Now, you actually did come across this at AS. You came across this in this guy. If I go to, what's the best one? You actually came across it in a dinitrile, in this one here. Butane dinitrile. Yeah. So this is the nitrile ending, and there's 2 of them. So this is a bute because there's 1, 2, 3, 4 carbons. It's an ane, but the problem is, you see, because it's a dinitrile, yeah, the dinitrile, the E goes back in. Now, the reason why you came across this at AS, there's no dash there, by the way. If you want to put numbers in, you can. This would actually be a 1,4 dinitrile. There you go, if you really want to be proper on it. But the reason why this comes up is because the E was there in the nitrile name originally. So when you came across a singular suffix, something like this, I'm actually going to draw that displayed now. It's nice to do so. Yeah, that's ethane nitrile. And the E is there, ethane with the E nitrile. And the reason being is you've got 2 ends next to each other and you need to separate them. Otherwise, it'd be ethane and a nitrile, which just sounds like you've got a stutter. So the E is there. Now, whenever you get any di or tri suffix, or tetra or penta, however you want to go, the E goes back in. Yeah. So this is cyclohex. Oh, sorry, with an E ending, because you don't want an E next to an E. Yeah, the A goes back. Sorry. Cyclohexa 1, 3, 5 triene. There you go. And the reason why it's an A and not an E is because you don't have 2 E's next to each other. Yeah, cyclohexa 1, 3, 5 triene. That is what I have drawn there. They are not the same thing. If you are asked to name this guy, then the answer is benzene. If you're asked to name this guy, then it's cyclohexa 1, 3, 5 triene. That is the proper IUPAC name for benzene. And those diagrams are very different. Be aware of this. Yeah. Now, I just want to explain the aromatic thing. So the word aromatic. So aromatic. Now, aromatic is a bit of a nightmare for me in A2 chemistry because students link this to the word smell. They know that if somebody says, oh, this is a very aromatic compound, they tend to refer that someone's telling you that it's smelly, that it has some kind of scent. Now, in this case, it does not mean this whatsoever. Yeah, the word aromatic now is talking about what's called delocalized stability. Yeah, aromatic. When a compound is stabilized through delocalization of electrons. Now, I'll explain that a little bit further now, because it's great to write down words like that. It doesn't really mean much. I'll explain now what this is talking about. So, when we first introduced you guys to alkenes, yeah, so you can all have a go at naming this guy, simplest alkene there is. Yeah, there we go. So when we introduce you guys to this one, which of course is ethene, one of the first reactions that we talk about with these compounds are addition reactions. Now, this is because they tend to go through addition reactions rather than substitutions, which we know this because the double bond is reactive. It can break open and we can add things to this. And one of the examples of this is you can add hydrogen gas. Now, this process here is called hydrogenation. Now, you can make a note of that. Nota bene, hydrogenation. Hydrogenation, the adding of hydrogen. Now, just to tell you that this is a reduction reaction. We're going to revisit this, I've no doubt, later on. But hydrogenation, now there are many methods of doing this. But the number one method of adding hydrogen to a compound is hydrogen gas, a nickel catalyst at 60 degrees Celsius. You have to know that for A2. So that's hydrogenation. So we're going to add hydrogen to this alkene. So when we add hydrogen to this alkene, we can even draw the mechanism underneath. Yeah, this is going to go through an electrophilic addition. This is EA. EA Sports. It's in the game. So we know that EA is going to be something akin to this. Yeah, so even though the hydrogen molecule is non-polar, this is a non-polar molecule, so why would it go through electrophilic addition? The reason being is on collision, when these molecules smash into each other, the electrons will repel each other and it will become a polar molecule. So non-polar, nota bene, becomes polarized on collision. Becomes, I should really shrink my pen there, becomes polarized on collision. Yeah, so on collision, the cloud of electrons surrounding the hydrogen, rather than being even, because the double bond is electron rich, this is electron dense. Yeah, alkenes are the double bond has a region of electron density. It's another key point there. I hate the different sizes of text, not that it matters. On collision, the cloud of electrons is going to shift. And this hydrogen molecule will become polar as a result of that collision. Now, once that happens, the double bond is going to reach out. Notice where I start. Yeah, making a really distinct point of this, guys. Yeah, whenever you're doing a mechanism, yeah, we're starting in the middle of that double bond. The double bond is breaking. So if you want to break a bond, you start in the middle. This now reaches out and goes to the hydrogen. This bond now needs to break. So you start in the middle and it goes off to that hydrogen. Curly arrows always move away from each other. Please note that these are not straight lines. This one isn't even a straight line. It is curly. Yeah, it's not like this. That's terrible. Yeah, but it is curved, and that's important. If it was a straight line, then they won't like you. Yeah, they'll deduct a mark for that. So at this point, we're going to form this compound. The double bond has broken open. I'm going to put the hydrogen onto this guy. I just wanted to. It was just a random choice, to be fair. We now form a primary carbocation. So this is a primary carbocation. Carbocation. It's very odd. Oh, I've suddenly realized I can't see any chat going on because I've got my little thing up. Oh, there we go. Okay. So I didn't actually need that. Yeah, I'll do. So I formed a primary carbocation. Right, and then of course the hydrogen is now going to become fully negative. Apologies, habit. All your charges must be circled for A2. And that's now going to hop onto that positive carbon. And there's the end of your mechanism. So what we're going to form in this reaction is we're going to form ethane. It's also nice to color code this. These are the original hydrogens. You notice that whenever you do an addition reaction with an alkene, you're going across the double bond. Yeah, these are the hydrogens that I've now added. It's gone across the double bond that was there originally. Now, we can measure the enthalpy of that reaction. Not the easiest reaction to measure, but it can be done. And when we measure this, we get a heat change of this, of a delta, stick with my pencil. This has a enthalpy change of, give or take, about minus 120 kilojoules per mole. Kilojoules per mole. There we go. So the enthalpy change for that reaction there is 120. Now, this is where the delocalized thing is now going to start making an appearance. So let's look at the next one. So what we're now going to do is we're now going to do another reaction with another alkene. Let's switch to, let's do this one. So I'm going to give you this guy. Right, guys, can you have a go at naming it for me? Remember that rule. Oh, apologies. There we go. Have a go at naming this now for me. Pause the video. Have a go at naming it. Come back to the video when you're ready. This one actually, by the way, is far more interesting. It still doesn't show geometrical isomerism, so don't worry about E and Z. We know that geo doesn't exist here because the carbons involved, this carbon here in this double bond, has the same group attached twice, so no matter what its orientation, it's always going to be the same. That's by the way, that's the explanation to it not showing geo. That question comes up a lot. So bear in mind that. That's one of the questions that repeats from AS in A2 because essentially students found geometrical isomerism difficult because it was a brand new type of isomerism that they hadn't come across before. So at this point, they didn't really like it so much. So they bring it back in at A2 at that point. Right. Okay, so I hope you guys have had a go at naming this. So number one, it's a pent. Oh, it's a diene. I now need to add the A back because it's a diene, and I now need to number it. Carbon 1, 2, 3, 4, and 5. So this now is penta 1, 3, diene. There we go. So we're just doing some practicing here, guys, of the organic naming. I'd love to see you guys contributing a bit more on the YouTube chat if you can, guys. I'd love you to do that. I'm just trying to get my computer to put both screens on for me. Can I now make my chat disappear on that window? Private chat? Oh, nope, that didn't work. Comments? Oh, can I just get rid of the comments? Nope, apparently not. That's irritating. Fine. I've got a million things now of me moving around. I don't really like that very much. Is it not Penta 1, 4? Oh, sorry. Thanks, Winkit. My apologies. Thank you, Winkit. Spotted the error. Easy mistake. Thank you. Do apologize. And you know what? It is nice to see that you guys can contribute on the chat. Although I didn't do it deliberately. It was a mistake. I even numbered them deliberately so I didn't make that mistake. Ugh. Yeah, just to explain where the numbers come from. It's a 1 because the first double bond is between carbons 1 and 2. The second double bond is between 4 and 5, and you always choose the lowest number, so it was 1, 4. Thanks, Winkit. Appreciate you being on the ball. Cool. So penta 1, 4 diene. So what we're now going to do is we're going to hydrogenate penta 1, 4 diene. So we're going to now hydrogenate it using nickel catalyst, 60 degrees, hydrogen gas, and I'm now going to need 2 of them. Yeah, this kind of makes sense. We can draw the mechanism out for this if we like. We could probably do them simultaneously if we wanted. Do I really want to do the mechanism? It's an awful lot of drawing, won't bother. And what we're going to form is we're going to form pentane. Yeah, all the double bonds are going to get broken, and we're going to form pentane. Again, I will color code this to show you where the hydrogens have gone. So these are the originals. These ones in black are the originals. And then the ones in red are the new attachments. Oh, now it's gone tiny. Laptop seems to be behaving okay at the minute. So these are the 4 hydrogen atoms I've attached. Right. So what I'd now like you guys to do is on the chat, please, can someone post what the enthalpy change of this reaction would be based on your understanding of the previous one? Yeah. Make a prediction. Prediction is always nice in chemistry. It's one of my favorite parts of chemistry, being able to take your understanding of a concept and being able to develop that simply by, well, if I understand that and I can apply it to this. Yeah, and that is so important for A-level. GCSE, not really required so much. It's very much kind of regurgitate. There's a little, the higher level questions, the 9 questions, the 8s and the high 8s and the 9s, level 8, 9 that is, tend to have a little bit of understanding in it, but it's still relatively rote learned. When you get to A-level, you now need to start taking your understanding and putting it into these contexts and these making predictions on based on your understanding. It's much, much harder. So I know that there's probably a lag on this. So, hey, Tenzi, he's on it. So, and he's absolutely right. So this enthalpy change here is going to be minus 240 kilojoules per mole. Thank you, Tenzi, for being on it. Thank you. And Tenzi, you are correct. Tick, smiley face. Hey, look at that. So the heat energy output from the addition of the second hydrogen molecule simply doubled the enthalpy change. This makes sense. If the first addition reaction was going to put out that much energy, then it would make sense for the second one to also do the same. So at this point, we now need to look at our third example. I'll switch back to black. So let's now do this one. Let's try this one. Everyone have a go at naming it. That would be grand. Have a go at naming this for me. There we go. So have a go at naming this one for me. So this is butte. It's a butte. It's a beauty. It's not a beauty. It's a buta. Oh, do you see what I did there? I'm gonna stop. The A goes back in because it's a di suffix, and it's on carbons 1, 2, 3. So the first double bond is between carbons 1 and 2. So that's buta 1. The second one's between 2 and 3. So this is buta 1,2-diene. Okay, so we're going to hydrogenate this guy. Let's add hydrogen to this. Once again, we're going to add 2, and we're going to form butane. Right, so on the chat, please. On the chat. Again, color code it to be able to see the original hydrogens that were there originally. It's an interesting picture, isn't it? Because now we've got this odd scenario where the hydrogen seems to go up and down on that middle carbon. But it's absolutely correct. It's correct. There we go. Oh, missed one. And there. Right. So this is now formed butane. Yeah, and the question is, what's the enthalpy change? So I'm going to put this to Winkit. Winkit, can you have a guess what you think the enthalpy change will be? Don't overthink it just yet. Just what would you expect it to be based on what we've been doing so far? I know that you're all sitting there thinking, Mr. Duncan is walking us into a trap. I am. You're absolutely right. Well done, Winkit. That's what I'd want. Right, the enthalpy change for this reaction is indeed minus 240. Delta H equals 240. Yep, well done. 240 kilojoules per mole. Nothing special as yet. So this was all kind of expected. When they were doing this in labs, they were like, yeah, this is cool. This does exactly what we think it'd do. And then this happened. This is the trap. So they then proceeded to do the next one, which was this one. Right, let's have a go at naming it. Once again, still no geo. I'm not saying any geos in these compounds because they're all covered in hydrogens. There we go. You can have a go at pausing the video and naming it for me. This is buta. It's an A because it's a di suffix. Buta, and it's on carbons 1 and 3. So buta 1,3-diene. And once again, they're going to hydrogenate it, and they had an expectation. Yeah, I've suddenly realized all my learning objectives are wrong on this lesson. I'm going to go back and change them. Understand aromaticity. Yeah, understand. Nope, not going to do that anymore. Changing it. Scrap it. Understand aromatic stability. Aromatic stability. Stability. And recognize when it happens. Be able to recognize when it occurs. Be able to recognize when it happens, when it's present. I like that. When it's present, draw aromatic compounds. I'll stick with that one. It's fine. I should be predicting enthalpy changes. Right, so this one, once again, we're going to form butane. I'm giving up on the color coding thing, by the way. It's taking me too long. No, change my mind. I'll put the sticks in. So these are my originals. No, they're not. That's not an original. Boom. See you later. See you later. Get rid of these guys. There you go. They're originals. And then all got these guys. Oh no. Pen size, all wrong. There you go. H there, H there, H there, and H there. Right. So at this point, once again, we're forming butane as an output. And Winkit, what would you expect? Expected. There we go. So what would be the expected enthalpy change, please? Delta H equals... It's hilarious. I shouldn't have asked Winkit. I should ask Julian. Julian, go! No, but he's going to have a big delay. The predicted was minus 240. Of course it was. Minus 240 kilojoules per mole. But it isn't. Actual. Okay, and at this point, this was the weird bit, you see, because they were like, what? What I should realize I should do is I should do that one in black because it's the expected. Yeah, minus 240 kilojoules per mole. There we go. And the actual, can I just point out, by the way, that I'm sorry if this isn't actually correct, but it's give or take about right. It's about minus 220. And at that point, they were like, it's lower than expected. Less than expected. Now, what does that tell us? Less than expected. What that tells us is that the energy gap is smaller. Thanks, Julian, for contributing. I appreciate that. Let's put this into a diagram of energy change to explain this. So if we were going to do, so number one, the reaction is exothermic. So we can put shelves on here. Yeah? So what we can always say is that the bonds in butane, we've done 3 reactions here, guys. We've done 3 reactions. Okay. Let's stick with the butane one. We've done 2 reactions with the same compound. I should have done the other one, but I couldn't, you see. I needed to make it longer. You'll see why in a second. So we know that the bond enthalpies, this is a bond enthalpy diagram, by the way. A bond enthalpy diagram. Enthalpy diagram. Yeah, and what this is showing is the strength of the bonds in the compounds. So down here is butane. Yeah, this is butane down here. And we know that the butane bonds are strong. Yeah, they're stronger than the originals. Students often get that really confused. They think, but it's gone lower. And I get that. I totally understand that, folks. Yeah, this is actually one of those tricky things. Yeah, let's call that energy level there. And I'm just going to, like, in a red line, go, there's the energy. It's not actually, it's actually enthalpy on here, by the way, guys. That's the trick to this, enthalpy. Now, the reason why it's lower is because we know that if you've got a set, this is where I need to go back, and if I want to explain that. Okay, I'm going to, just for clarity here, folks. Yeah, if you start off with A bonded to A and B bonded to B, yeah, in order to break those bonds, I'm going to raise them up in energy. This is the delta H to break the original bonds. Yeah, break original bonds. Bob, I like it. Now we've got A, B, and B. All bonds are broken. Then new bonds are now going to get made. Boom! New bonds are now being made. So this energy here, so this part, the first bit, of course, was endothermic because I had to add energy. Yeah, that bit's endo. Add delta H plus. Yeah, oh, that's my laptop telling me my lesson's coming to an end soon. We've only got 10 minutes left. And this one is exothermic. Yeah, and what you realize is that the energy being released by the new bonds, which are going to be A bonded to B and A bonded to B, the heat energy being released in the new bonds being made is way bigger than the energy required to break the original bonds, which means these must be stronger. The stronger your bonds, the more energy released. Yeah, hence why it's lower, because they've lost energy. There's energy literally being lost, which is here. That's the enthalpy change of the reaction. The overall energy change between the bonds being broken and the bonds being made. Yeah, so the bonds are getting stronger. So what that now means is we now need to link this back to butane. So what we now need to realize that we started off, this is now going to be butane down here. We're making all of these bonds. Yeah, and that's always the same for the last 2 reactions because we have the same bonds being formed at the end. So the enthalpy level will be exactly the same. This is the last two reactions that we covered. I'll highlight those again in a second. So this is for these two here. Now, here's the thing. So this number here, these two numbers represent the difference in the energy levels. So what that means is it's this gap here. So when we started off with a buta-1,2-diene, this guy, when we started off here, yeah, there and there, when we started off here, the difference between those two was 240 kilojoules per mole. That was the gap. But however, when we then had buta-1,3-diene, the gap was smaller at 220. What that tells us is that the bond enthalpies in the diene, that diene, are more stable. Yeah, the bonds are stronger. The bonds are stronger in that diene than it was in the 1,2-diene. And we now need to explain why. And the reason is the gap between them is perfect for pi overlap. Let me explain what that means. So this is where we go into the structure of an ene. So we know that if you look at, we've been drawing alkenes like this for years. I'm going to draw propene. And what we realize is there's all kinds of cool stuff going on with the bonds here. What we can now do is break this into the different types of bonds present. So in reality, this stick diagram actually looks more like this. We've got a sigma overlap between that one, a sigma overlap there. Sigma, by the way, literally means head-on overlap, but this is a sigma bond. Yeah, which literally stands for head-on overlap of orbitals. Yeah, but then we then had sigmas over here, sigma to the hydrogen, and then a sigma to that hydrogen, and then a sigma to that hydrogen. Yeah, and then we had a sigma to that hydrogen there, and then a sigma to this hydrogen over here, and then a sigma to this hydrogen over here, and then we had a pi, which this is the weird bit. So I haven't orientated this very well. I'm gonna have to reorganize this. So I'm gonna delete that there and delete him, and then I'm gonna move this guy, because this guy now has a shape, which is like this. There we go. So I can now do this. there's a sigma here, there's a sigma to this guy here, and a sigma to this guy here. Right, where does the pi bond now come in? Because these here represent the single bonds. Here are the single bonds that we're seeing in our molecule. Yeah, I'm going to translate that out into this diagram, into this stick diagram here. Yeah, so because it had a double bond. Yeah, we're seeing the single bonds here, guys. Yeah, and then the CH3 down here has also got a shape of tetrahedral. Yeah, there we go. So that's what I've drawn here. Now we need to represent what's going on here. Where's the second bond? The second bond is a pi overlap. So we have a split off p orbital. I'm going to make that a bit bigger. We've got a split off p orbital here, the py. And what happens is the py's go up and down and they overlap here and here. This is called a pi bond. Yeah, this is a pi bond. The overlap of two p orbitals. Yeah, and it's the sideways. You can actually write that. So this is a pi bond, which is the side overlap of two p orbitals. Yeah, in this case, the py. So that's just the standard. So that's one double bond. So what now happens when there's two? So we need to explain why this one didn't do it. This one didn't show any extra stability. Yeah, this one didn't do it. And the question is why? So the reason why is because this is going to be really hard for me to draw. We've got our single bonds in the middle. It's going to be really tough, this. And we have a pi overlap here. We have a pi overlap on this one. But the thing is, though, this carbon atom here has also got to form another set of p orbitals, another set of overlaps. And what's now going to happen is that you're going to get this here is the py. This is the py orbital. We're now going to have a px orbital splitting off. So this is like horizontal, really hard for me to do this without model. Molly mods are amazing for this, by the way. So what you actually have, to make this clearer, you have this vertical overlap in the carbon atoms. The vertical overlap, yeah, which is this one here. I'll do that slightly better. You have a vertical overlap here between these guys, and then in the next carbons, what you have is a horizontal overlap through that way. So these overlaps are literally opposite to each other. Yeah, so if I do that with my hands, this is where the camera comes in handy. One's doing this and one's doing this. Yeah, so one's in a PX, one's in a PY, the next one is in a PX. So they can't link together. Now, when you now get the next situation where the double bonds are separated, here's what now happens. The double bonds are now one carbon apart. And what this now leads to is a really cool effect. Because what we can now do is we realize that when we draw this out in terms of the P overlaps, we get to see this. We get to see a PY here, 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 PY here. And what you realize is they can overlap all the way across the molecule. And this is delocalized stability. So they're all happening in the P direction, the P orientation, the P direction, sorry, the Y direction, Y-axis. So we have this huge set of overlap between all of these P's are now linked together in one giant overlap. And then you can actually draw on the hydrogens, then stick out. By the way, this is completely flat, this molecule. So this hydrogen's now coming out flat as well, and that one's going to be going off that way. That one goes, this molecule is completely flat. Yeah, it's planar in its arrangement, like this. But now the electrons in these orbitals, yeah, can now flow through the entire structure. They can flow all the way around this, and it provides additional stability. So in order to get, nota bene at this point, nota bene, delocalized stability, stab, stability occurs when double bonds, when CC double bonds are separated by one carbon-carbon single bond. And you get delocalized stability. So I know that we're at the end of the lesson now and I'm running right to the wire. So just now realize that there are now 3 double bonds and they're all separated by one single double bond. All of these are now delocalized. We're going to have a really amazing pi system, which actually now has a PY, a PY, a PY, and every single one of these is going to overlap with the other. We end up with this amazing delocalized system where the electrons can flow all the way around the ring. You end up with this. You can imagine the hexagon shape and a donut of electrons above and below the system where the electrons can flow all the way around, providing it with additional stability. We'll pick this up again next time, guys. I'll end the lesson there. Definitely didn't manage to do any of the learning objectives I wanted, but I felt like it needed to be done. So I'll change my learning objectives on my YouTube video as well. But I'm going to end the lesson there. Let's go back to this one. I'm trying to figure that out. There we go. Right, guys, I will see you guys next lesson for benzene continuing, and I'll see you all soon. See you later, guys. Hope you found it okay. See you later.